Hey everybody. So I want to start off this discussion with this particular research paper, which is where my experiments started, and it's called Lazy Diffusion Mitigating Spectral Collapse in Generative Diffusion-Based Stable Autoregressive Emulation of Turbulent Flows. It's an awfully long name, put out by UC Santa Cruz on yesterday, December 10th, as I'm making this video, December 10th, 2025, and then so essentially, like what they do is exactly explicitly what the title says is that they mitigate spectral collapse, right? In generative diffusion models, and then so the to give you an idea of that concept overall of like what is spectral collapse. Spectral collapse is like the most common example that people think of when they think of AI is that like it makes like six digits and like of hands, right? And um, can't make hands right, etc. And that was true for a long time because of this problem specifically, right? Where so when the model tries to focus on those fine details, like essentially like how many digits like are on a hand, that can become blurry over time and via the training. And the reason why that becomes blurry to the model is as they outline this concept of spectral collapse. And then so they design a method to mitigate this, and they point out that this is all based in geometry, and they mitigate it using geometry, which is where it piques my interest and intrigues me within this. And then to me, it's like, okay, well, if they're like, with often, I mean, just my opinion on these research papers, like they're taking it there, but they could take it one step further from there, right? Which is that so like you can do more than mitigate the problem. Like if you can tap in and get access to this, which they present in a 31-page research paper very nicely, showcasing that you can and exactly how to do so, then what you can do as a step from there is essentially like inject geometry into the system, and then so you can not only mitigate spectral collapse, you can prevent it, but then you can also make the models better, right? Like you can inject geometry into models that aren't experiencing spectral collapse, which would be extremely beneficial, etc. overall. And then so that's essentially literally what I've done within the experiment here. And then so I call the end result of this overall Geometry LoRA, and that's exactly what it is, right? And then so the end result of this is training a LoRA on a like only on the geometry of a data set and nothing, like never being given the data set directly, labels directly, etc., right? The goal is, and then so the goal with this, like the end result would be that you would utilize this to like buffer the model's like capabilities when it comes to uh, LoRa. It's essentially like essentially what I'm showcasing within this is that I can utilize geometry as a LoRa very specifically, and geometry loss as a LoRa to turn, or like within LoRa's to turn the dial of LoRa training specifically, and that's what I'll showcase, and I'll showcase it all within here within that for you. But so let me dive into this and kind of the background of this experiment and of this paper, relating it to the paper, etc. Right? And then so within this, my experiment that I ran was the Geometry LoRa experiment, and then so the core problem within all of this, as pointed out by the Lazy Diffusion paper, is that AI struggles with physics. So a recent paper called Lazy Diffusion exposes a fundamental weakness in how modern image generation AI handles physical systems like turbulence, smoke, or fluids. The problem is that diffusion models, such as those behind like DALL-E or Stable Diffusion, are effectively nearsighted. They capture large, smooth structures well, but they struggle with fine details. And then so why this happens is that during training, noise is added in a way that destroys high frequency information too early in the process. So once these details are gone, the model can no longer distinguish real structure from random noise. How many fingers does a human hand have? The model doesn't know because there's too much noise added into the beginning of that process continually and over enough times for the model to not learn that it has five fingers. So The result is that this leads to spectral collapse. Instead of sharp, physically accurate motion, the model just produces blurry, unlisted blobs where that should be, right? It doesn't know. And then so, in short, the model loses the underlying structure of the system that it's trying to simulate. The paper's fix is called lazy diffusion. And then so the researchers proposed two key improvements. One is a power law noise scheduling, which is the noise process was adjusted so that fine details survive longer during training, forcing the model to learn them instead of losing them to randomness. And then two, lazy diffusion is a one-step generation process, and that's kind of their magic formula within this, right? Instead of generating images through hundreds or thousands of tiny steps, which accumulate error, the model's trained to jump directly from a noisy state to a clean result in one single step. And so the outcome is that these changes allowed the model to generate stable, high fidelity turbulence that actually obeys physical laws. The key lesson from the paper is simple but powerful. Preserving structure matters more than adding more computation. And that's the bottom line within this, right? This method that they introduce does strip a lot of the computation from LoRA training overall, right? Like LoRA training methods overall are computationally expensive, right? And then so anything that you can do to decrease the computational expensiveness of LoRa's saves you time, money, effort, etc. in the long run, and that's exactly what this does. This is like sparse LoRa, essentially, is what their method is, and so it's cool in that regard, right? But to me, you can extend it further beyond just this sparse LoRa or lazy diffusion method. And then the idea that I come up with is geometry LoRA, or the geometry LoRA hypothesis, which is that this experiment takes that same insight, that structure first, and applies it to a different problem: how AI represents and generates shapes. So the guiding question is, if models fail because they lose structure, what happens if structure is enforced explicitly? So they're saying, so here's model collapse, here's spectral collapse, here's how to mitigate it. And then so I'm just saying, and then it's all geometry based. And then so I'm okay, what if you just inject the geometry directly into it, right? Which I've done kind of a lot. And then so the core idea is that instead of letting a model discover structure on its own, which often produces tangled, unstable latent spaces, the geometry of the data is computed first. And then so in this particular instance, I use PCA, or a principal component analysis, which is used to build a clean two-dimensional geometric map of the data set. And then this map becomes the ground truth structure of the data, pointing it out 100. PCA is not implicit or required within this, right? It's a PCA is just the way that I'm utilizing to represent this particular data set that I'm going to showcase to you, which is digits overall. If it were a different data set, I would use something different than PCA, highlighting that, right? And then so why the geometry LoRA? So LoRA is, or low rank adaptation, normally injects new behavior into a model without retraining it from scratch. And then so in this case, what's injected is geometry, and pure geometry, right? And then so no images directly, and then no image labels. And then so the result is a geometry structured autoencoder. The encoder is forced to map each image to an exact location in the predefined geometric space, and then the decoder learns to generate images only on those coordinates. And then so the model is no longer free to invent its own latent structure. It must obey the geometry that's given. And then so the experiment and what happened. To test this idea, the decoder was given nothing but 2D coordinates. No image input, no labels, and no class names. What emerged was surprising. There was a clean synthesis. The model generated clear, recognizable digits utilizing geometry alone. Knowing where something exists in the geometric space was enough to recreate it. This created physics-like continuity. moving smoothly through the coordinate space didn't produce simple crossfades. Instead, these shapes morphed naturally, meaning I can utilize this to also impact video and create video, not just images. So in this, I'll showcase the video for you, and then some. This behavior mirrors how real physical systems evolve continuously rather than jumping between states. The bigger implication within this is that geometry is the stabilizer. This experiment points to a broader idea. Geometry can act as a stabilizing force for generative AI. Instead of retraining massive models to learn structure from scratch, it may be possible to inject that structure directly, much like a LoRa, but for geometry. As far as potential applications for physics simulations, injecting a turbulence geometry could prevent diffusion models from collapsing into smooth blobs. In terms of animation and characters, a skeletal or kinematic geometry could enforce consistent motion, preventing disappearing limbs or broken poses. And then on any structured domain, wherever AI struggles with hallucination or instability, explicit geometry may provide guardrails. Essentially, the bottom line within this is that, like, if you want to make sure that your images, your videos, images, etc., are smooth, like actually obey physics, like actually bodies actually have skeletons, etc. And then that's what this framework gives and does, right? And then so the final takeaway of all of this is that the experiment demonstrates that the explicit geometric constraints can dramatically improve generative stability, exactly what I laid out, right? And so rather than asking AI to discover structure through brute force, it can be more effective to give the structure directly and then let the model focus on expression instead of invention. And then so in that sense, Geometry LoRA isn't just a trick. It's a shift in how generative models can be guided to respect the underlying reality of the data that they work with. And then so diving deeper into this notebook very specifically, and then into the experiment over here. So I ran multiple iterations of this experiment overall, right? So this started like with, I'd say like maybe 4 or 5 notebooks before this overall, just highlighting that. And then so oftentimes like a daily, I will run experiments that never get showcased like ever or anywhere on this channel, right? But so within these experiments, so we start and I run it for 50 epochs. The loss is very good, right? So the model is learning the shape, and then as we can see here, here's the shape. It's like it is learning, right? Like very, very nice. Like there's a 0 in front, and then we're getting to like 0.5, which is good. And then as we can see here from that, like testing that out, this is exactly what we would want to see, right? And it's not perfect, like, but so here's 0. I don't know, I'm not sure. 1, 3, 4, 5, 6, 7. I think 5, and I think 9, right? And then so that could be 8, 7, 8, 9, 9, right? So and then so 6, 7, 8, 9, and then so within this over, like, so the bottom line is like these images and these digits are what I just went over here on the document, right? Where the model was trained on like just the geometry alone, like the underlying geometry of these digits, and then never like ever given these digits, given this, right? Like these like what we're looking at here is what the model was given, like, because it's essentially like it was given a 2D PCA representation of digits, right, of this data, which is this, and then it produces the images off of this once with enough essentially like with the digits off of this with enough geometric pressure, like enough geometric guidance, right? And then the next step within that I want to showcase, and the next step within that would be utilizing that to actually like create video, right? And then so here we go. It's not perfect by any means, right? The zero is 100% the clearest. So there's a 5, like 3, 1, 5, 7, 9, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, again, not perfect, but like, and it's the point is to phase it over time, right? Like you don't want it to be perfect, like, but you can see digits within here very clearly, and the digits morphing, right? And that's the goal. And I do see it 100% morphing. And I've seen 3 to an 8. Okay, I've seen every digit that it is morphing to once you pay enough attention to it overall, right? And then so again, same thing within this. This is just proving the concept of geometry injection to create, improve, etc. video. And then so in this instance, this is just like pure geometry injection, nothing else, right? So imagine that you had like actual video, actual training before this, and then on top of this, and then you're just layering this like on top as like the coup de grace. Like that's where this is most powerful within this. It's like the end step result, right? So you have your like your tuning and your training. So in the LoRa in this instance, or like, you know, if you're taking a step up, like DPO, GRPO, whatever it would be in that instance, and then like after your reinforcement learning steps within that, or your training steps within that, like at your very end, your very last training step within this, you do a geometry injection just to make sure and like buff the geometry like in the areas where like you want it to go, right? Make sure that there's no dents anywhere where you don't want there to be dents, and just kind of like puff those out. Or maybe just like, you know, like make sure that some divots are more carved out than they were before, etc. And then so that's kind of the overall gist of that. And then so that's kind of the overall takeaway from this. I'll leave a link to this here. This is also, I'll leave a link to this too, which is also, I didn't go over here, but this is kind of just a more like detailed breakdown of this, and it's only 3 pages, right? But so I'll leave a link to all 3 here, the 2 documents, as well as the collab and the paper here. And then so if you like this type of content overall, please like and subscribe. Thank you very much.